So let's go ahead and get started. A few quick reminders before we jump into the talk. First of all, this is a bi-weekly seminar series, so tune in again in about 2 weeks for another speaker. And in terms of the logistics of this, make sure to mute your microphone while you're not speaking so that we don't get a buildup of too much background noise. If you want to ask questions, either unmute yourself or you can ask it in the group chat or something along those lines, and we'll make sure that question gets addressed. We'll also have time at the end for questions as well. So today we're lucky to have two speakers. We have two co-presenters talking today. Jan Rybizki, who's a postdoc at Max Planck Institute for Astronomy and did his PhD at the University of Heidelberg. And then we also have Oliver Philcox, who's a graduate student at Princeton and did his master's at Cambridge. And you two have been working together for several years, if I'm correct, since 2017. And they're going to tell us today about inferring the Milky Way stellar initial mass function using chemical evolution modeling on multi-star elemental abundances. So take it away. If you all need help figuring out how to share screen, oh, you've got this. Okay, so take it away. Thanks.
Thank you very much. So I will start talking, and then Oliver will come in. He's master of the slides for the moment. I want to say that I'm very grateful and thankful that we can present here our project to such a specialized audience, and that we can do it online. And one thing, if I run away, don't worry. It's just my kid is sleeping back there. In Europe, it's already sleeping time, so don't worry. Oliver will take over then. And yeah. Otherwise, everything should run fine usually. I wanted also to say that we are only consumers of nucleosynthetic yield tables. So we are really, I would say I'm ignorant about the nucleosynthesis and how big stars or about supernovae and what they create. But yeah, we are using them and we are mainly playing around with them in a mathematical or statistical framework. And we want to show to you how we approach this, and hope that we can learn a lot from you. And please just interrupt if something is not clear. So today the main focus is on a paper that appeared recently. It's inferring. Yeah. So here's the outline of the talk. We will talk about galactic chemical evolution models, and just because we produced that, it will be with the example of Chempy. We will show you how we could choose yield tables or optimize yield tables for hydrodynamical simulations and optimize the parameters. Then we show you how a framework how to score nucleosynthetic yield tables. So that might be quite interesting, because we could, with the galactic chemical evolution model in between, we can directly go from the yield tables to the data and see how well they are reproduced and give a score to it. And then yeah, we improve upon the previous projects by putting more than only one star into the inference, and that leads to a big potential of new projects. Okay, next slide. So fast and flexible galactic chemical evolution model, Chempy. So what does Chempy do? It takes nucleosynthetic yield tables, for example, from core collapse supernovae, from supernova type 1a, and from AGB stars, and some SSP parameters. By SSP, I mean simple stellar population, and parameters for the simple stellar population are the IMF, which we use here, and the number of stars that go supernova type 1a, basically. And from those ingredients, IMF calculates an IMF integrated and metallicity dependent yield over time. And this can be used for any chemical evolution model or hydrodynamical simulation. And how does this look like? So for in solar metallicity simple stellar population, you would get feedback of over time. So time is on the x-axis, and the fractional feedback is on the y-axis. And in the top, you see the masses of stars when they are dying. So an 8 solar mass star would die after 40 mega years, and then a 2 solar mass stars after 1 giga year, 1 solar mass star after 10 giga years. And you see here the contribution from the net yield from core-collapse supernovae for carbon and oxygen, and for 2 different yield sets. They are quite old in the literature. It doesn't really matter. It's just to show that there can be quite dramatic differences between different yield sets. And of course, if you add other channels like supernova type 1a and AGB stars, the AGB stars kick in later after the supernova stars contributed, the core-collapse supernova, and the supernova type 1a comes even later but contributes a big fraction of iron, as you can see. Here, what we display here is the cumulative yield. Do you have any questions up to here, or anything? If not, I would just go on. So Chempy takes now these integrated yield tables and the simple stellar population parameters and the ISM parameters, and outputs ISM abundances over time. So really, what we think of as what Chempy is a black box. You put in yield tables and some parameters, and you get out the ISM abundances over time for a one-zone model. And usually, I don't even look inside this thing, but just to make it more graphic, this is how the one-box model works. It's just a one-zone model. So there is the ISM, and it's well mixed. It starts with hydrogen and helium abundance. And then stars are forming according to a star formation law, according to an IMF. They explode, go supernova, and enrich the ISM. So the thing is recycled into the ISM. And then you also get outflows. So it's a little bit more complicated. You have a second zone, a halo gas, which is also well mixed. And from there you get infall into the ISM box, and then new generations of stars are formed. So it's going on, and you even have cosmic inflow. So it's just to show that all those parameters can be tuned, but usually we keep them fixed. But what you see here, so a well-represented model by this would be a dwarf galaxy, but you can also, we usually plug it, use it for the Milky Way, but of course we don't reproduce any gradients or radial migration or anything. And then many generations of stars are formed. You get the ISM abundances over time, and you can compare them to observational data. When I say observational data, these are abundances of elements, and sometimes you have ages attached to them, or usually we would say you have ages attached to the star with the solar with their elemental abundances, and you can compare to the abundances that Chempy predicts. And here, for example, we have in this plane you have the alpha over iron on the y-axis and the metallicity on the x-axis. And in black, the apogee red clump sample, and for red, a model that was optimized to reproduce solar abundances, and then just an age sampling of the red clump stars, and you see that it's broadly consistent. And this is one thing about Chempy, there's no fiducial model for this chemical evolution model. It's asking for input data, and here we just put the sun, and then you automatically obtain galactic chemical evolution parameters. Okay, so now we put this into a Bayesian framework just to illustrate how this works. So think of Chempy as a box you put in as a simple stellar population parameters, and here we mean the initial mass function high mass, the high mass slope of the initial mass function and the number of supernova type 1a. And then the ISM parameters, which are the outflow parameter, the star formation rate, and the star formation efficiency. You plug them into Chempy, plus the yield sets, of course. You get the ISM abundances. You compare them to observational data and calculate the likelihood. And then you sample this in an MCMC until it stabilizes, and you get the best simple stellar population parameters and ISM parameters out of this. This is basically how it works. Okay. So now the question is, can Chempy be used to determine GINA-CEE parameters for hydrodynamical simulations? And we showed that in the paper that we did with where Oliver, which Oliver was the first author of. And the goal was to predict the best simple stellar population parameters for hydrodynamical simulations to make sure that they are consistent with observations. So what we did, we used Chempy we plugged in the same yield set that Illustris TNG was using into Chempy, and we asked which are the optimal SSP parameter, simple stellar population parameters, in order to reproduce protosolar abundances. So now, if we run the simulation, it optimized the two parameters, the Heimer slope of the IMF and the number of supernova type 1a. And before we did that, the Illustris TNG abundances looked like this. So you again have the apogee red club sample in black, and the Illustris TNG, the Milky Way-like simulation, looked like the spur that you have above. So they are over predicting. So the alpha enhancement is much too strong. And then we took the exact same thing. It just changed the Heimer slope of the IMF and the number of supernova type 1a and to the values that Chempy predicted, and ran the simulation again, and it went straight through 0, 0. So yeah, it's much better now. And of course, the problem is that you cannot just change the number of supernova type 1a or the Heimer slope of the IMF, because the other feedback models of this hydrodynamical simulation need to be fine-tuned. But it's just to show that in principle, you don't need to run a fully fledged hydrodynamical simulation to optimize these parameters. You can explore this parameter space with very cheap Chempy. So it only takes 1 second to run. And it's much cheaper than running a fully fledged Milky Way simulation. Okay, and we only used a single star to constrain this. Exactly. And I think now it's Oliver. Are you taking over? Okay.
Okay, so one of the most important, or the single most important hyperparameter for Chempy is the choice of nucleosynthetic chemical yield tables. So these are the yield tables describing the amount of metals, hydrogen, helium we get from type 1a supernovae, core collapse supernovae, and AGB stars. And as one of the earlier plots elucidated slightly, different yield tables have very, very different predictions. Even if we look at the abundances of a star like the sun when it was born, we find that the abundances are a very strong function of which yield tables we put in. So for example, the plot I'm showing here is comparing the simulated protosolar abundances from Chempy for 5 different choices of yield tables. Now the little green plots, the green dots in the middle, they are the actual protosolar data. And we notice that there's huge discrepancies between the different yield tables. They each predict very different things. And in particular, some elements are really not well understood. For example, magnesium, pretty terribly predicted, always, and also silicon. So this indicates that we need to be very careful when choosing our yield tables. And also, when somebody predicts a yield table, it's not a priori obvious how well it actually can be used to represent real data. So what we thought about is, can we devise a method to tell us which yield tables are the most useful in a galactic chemical evolution context? So effectively, yeah, we want to rank nucleosynthetic yield tables by their ability to reproduce stars like the sun. So how do we do that? We do it in kind of a similar way to before. We take the Chempy function and we try to compare Chempy observations to the true protosolar abundances. Now, as we said before, Chempy depends on a number of parameters controlling things like the mass function slope of the initial mass function and the number of type 1a supernovae exploding. So there's normally around 5 key parameters describing this. And for the purpose of this inference, we're trying to work out which yield tables perform best. So these things are really just nuisance parameters. So the best way to deal with it is just to marginalize over them. Say we don't have complete knowledge about how many supernovae explode, so let's just marginalize. Now, one other thing to note is that our model is not perfect, and it's not expected to be perfect. it's a very strong simplification. As Jan showed you from the plots earlier, just involving kind of boxes of gas and inflow and outflow, we're only really considering our universe comprised of 2 different boxes of gas. So there's bound to be some inaccuracies. So what we did is we theoretically included an extra term, a model error parameter, which accounts for some model inaccuracies at lowest order. It does assume that all elements have the same error. That's something I'll touch back on later in the talk. But that allows us to be slightly robust to the fact that our model is not perfect. Okay, so once we've got this, how can we actually compare models? And what I mean by models in this context is predictions from Chempy using different chemical yield tables. So whether we take the supernovae tables from Chempy or the supernovae tables from Nichols-Prantzos, for example. So we use 2 prime statistics to compare this. Number 1 is so-called the Bayes factor. So this is pretty commonly used in statistical model comparison. Effectively, you take your posterior, which is just the likelihood of protosolar observations given the Chempy model, and a prior, and we simply integrate it over all the parameters. So theta here represents the parameters controlling the 3 parameters, which are like the initial mass function, slope, number of supernovae, stuff like that. So this really gives us an idealized probability of a model. So in order to compare models, we simply look at the ratio of their Bayes factors. Another way we thought about to compare things is cross-validation. So the idea with this is that our Chempy model is predicting, say, 8 chemical abundances. So what it's doing is it's saying, I can predict you the chemical abundances of the first 8 most abundant elements at the time of the stellar birth. Now, really what we do in this method is that we only use n-1 of these elements, and then we perform parameter inference to obtain the best parameters, and then we use those best parameters to predict the other element that we haven't been including. And effectively, then we can compare this to the actual data to get an alternative likelihood. I mean, the fine details of this aren't particularly important, but the kind of take-home point is that we have methods which can robustly compare different models, taking into account the fact that we don't completely understand that we don't fully know the values of these crucial parameters, and a model doesn't have to be perfect. So what does this give you in practice? So this is a little excerpt from one of the tables, which shows the Bayesian scores, so from the first method I discussed, for a set of 5 different nucleosynthetic yield tables. So each one of these tables gives predictions for the yields of different elements as a function of mass and metallicity. It's just given the abbreviations here, but they're from a number of years, back from Chieffy's tables of 2004, all the way up to Nichols-Prantzos ones most recently. And you notice that the scores they get, which are effectively logarithmic, to give you some idea. So there, a small difference in the score is actually quite a large difference in how well the model works. We notice that the Nichols-Prantzos yields are significantly better than any other tables, as you can see by the score being significantly larger. And this does tell us things, actually. So one thing to note is that Nichols' yields are for rotating stars. They're the only set of yields we considered which consider rotating or collapsed supernovae. In fact, the rotation is as a function of metallicity. He has some prescription for how he determines that. We notice that simply by including something like that, we get far better predictions, and we get out, in our chemical evolution model, abundances which much better match observational data. So from this, you can kind of see the utility of the sort of Chempy framework in telling us how good our yield tables are. So once you've produced a yield table, we can tell you, yes, this is good and it matches observational data, or no, it's actually not particularly useful in our context. So that's quite a useful diagnostic tool. Okay, so one thing to note is that everything we've talked about so far has assumed that we're only comparing data with a single star. In fact, all the results from that entire first paper have only used data from the protosun, by which I mean the stellar abundances at the time, the solar abundances at the time of stellar birth. There's a couple of post-birth changes you have to be careful of, but there's relatively robust physical models for that. So that led us to thinking, well, I'm sure we can do this better. Let's see if we can infer these important parameters using a large number of stars. Now, immediately you might think this isn't going to be difficult. You just repeat the analysis, but suddenly instead of one data point, you have 100, say. It turns out to be slightly less trivial. The reason for that is that each star is different. And first of all, each star forms at a different time. So the function of Chempy, as we've sort of been banging on about, is to give you the ISM abundances at the time of the star's birth. Now that's difficult when we have 100 stars, each of which forms at a different time. To make things even more fun, each of them forms in a different location in the ISM. It simply isn't true to say that the evolutionary environments are the same for every star. For example, some of these parameters are things like the amount of gas flowing in and out of a region. We expect that to be spatially variant. Or the star formation efficiency. So effectively, how much stars do we form from a given volume of gas? So we have to take this into account. And it means that suddenly from having 5 parameters that we're trying to vary, we now have of the order of 400. That's not easy. And even things like stellar birth time. Now, one might say, okay, why don't we just use model stellar birth times? We've got catalogs of this. Problem is, it's not certain. Even our best models for the ages of stars only give you the ages to within kind of 20%, 20 to 30%. And we need much better precision for that. So in fact, what we have to do is we have to treat the age of the star as a free parameter, and we have to marginalize it over it. What I mean really is to say, we've got some estimate for how old the star is. So we'll take that as a prior and then just marginalize over the age to give us the best possible estimate without the bias of assuming the age is actually 20% different to what it truly is. Okay. So as I said, this is a pretty high dimensional problem. So effectively, we're trying to do 400 dimensional Monte Carlo sampling. Now, for anyone familiar with Monte Carlo and Markov chain Monte Carlo in particular, this is pretty difficult. So we have a solution, and it's a 2-part solution. Number 1 is actually using a little trick from machine learning. So the Chempy model itself takes a set of input parameters and returns chemical abundances, but each single evaluation of Chempy takes around 1 second. Whilst that's pretty quick, I mean very quick compared to something like a full hydrodynamical simulation, which is taking many hundreds of thousands of CPU hours, it's not quick enough for our purpose, because we need to sample this thing many, many thousands, if not millions of times. So what we actually do is we replace Chempy by a neural network. And the reason this works is that Chempy is effectively a black box. There's a lot of physics goes into the internal of it, but the user doesn't need to know that. So what we say is we train a neural network to take the input Chempy parameters and simply predict the output Chempy abundances. Effectively, it just acts as a fast, nonlinear interpolator. That's all. It's a high-dimensional function interpolator. It takes 5 inputs and does about 28 outputs generally. As many outputs as we want elements. Okay, so that's good. And the neural networks, I can go into lots of detail, but I'll spare you that, work very well. And the error on the neural network prediction is much smaller than the observational errors of our data. So it's a perfect approximation for our purposes. The second thing we do is we investigate some slightly more interesting sampling methods. So for those of you who are familiar with Markov chain Monte Carlo, effectively, this is a way of sampling posteriors by randomly jumping between points in space. This is quite inefficient, and if you've got more than, say, 10 dimensions, it's actually very, very slow to converge, and there's no guarantee it will converge, ever, even if you had infinite sampling time. Hamiltonian Monte Carlo, however, does much better, and the prime way it does this is by taking a function and also evaluating the derivatives of the function as well. And the reason this is better is because it allows you to preferentially sample regions in which the posterior is big. So by using this technique, we're able to sample very high dimensional posterior and actually do this inference with a 400 dimensional parameter space, which is great. Okay, so how does this actually work in practice? What we're going to do is we're going to test it in 3 different ways. Number 1 is kind of the vanilla test. It's to say, let's create 200 stars with known chemistry and known physics. And the Chempy model has some basic physics in it, and we're going to use this model to create some mock data. And this mock data set is simply 200 stars born at specific times with specific protostellar abundances. For all of these, we add observational errors to make it kind of realistic, to make it match contemporary data sets. Okay, so this is good to test that our inference actually works. So the idea of our inference is to estimate the initial SSP parameters which came into it, which are the kind of key hyperparameters controlling galactic physics, like the slope of the initial mass function, telling us effectively how many large and how many small stars we have formed. We know this because we put it into our mock data. So if our inference fails this test, we know it's not working. If I put in 10 supernovae per billion years, I should run our inference and we should say, okay, we get 10 supernovae per billion years. Okay, so that's test one, which we expect to work. Test two is slightly less trivial. This is saying, why don't we create mock data, but create it with one set of chemical yields, but analyze it assuming a different set of chemical yields. And this is important because if we want to apply such analysis to observational data, we don't actually know the chemical yields. As I'm sure you're all aware, yields are quite up for debate. And whatever analysis we do, the yields at some level are going to be incorrect. So this is an interesting test. How much does it bias our inference? The third test is to use mock data drawn from a different simulation. So for this, we use Illustris TNG. Now, Illustris TNG is a gigantic hydrodynamical simulation. It's been run over millions of CPU hours, and this includes far more types of physics than our simple simulation. Our simple simulation is just 2 boxes of gas. Illustris TNG is a full set of many galaxies, each of which are resolved down to kind of about 1 million solar mass resolution. So we expect the physics is going to be very different. So the real test of inference 3 is, are we biased by our model using different physics? For this, we assume the same yield set, so we can actually properly distinguish between what effects are causing what. So what effects do we have from the wrong physics, and what effects do we have from the wrong yields? Okay. So our three parameters, which I've just been saying, are the high mass slope of the initial mass function, telling us how many large stars and how many small stars we have, and the total number of type 1a supernovae. There's a couple of additional complications. Number one is something we call the model error. Now I touched upon this earlier, but this is worth revisiting slightly, and we took a lot more updated prescription for this paper. And we said, okay, we know that our yield tables aren't perfect. So for each output ISM abundance, we're going to affix an error for every element. And this error comes from some prior distribution, and we can marginalize over it. And this is actually turns out to be particularly useful, because not only does it make our analysis slightly more robust to having incorrect chemical yields, it also enables us to tell us at the end which of the elements are the most constraining. Do we have some elements which don't have any constraining power at all because the predictions from our model just don't match the data? So it gives us an indication of where our model is going wrong. I'll touch back on that in a couple of slides. The other parameters, ISM parameters and age per star. So these are local parameters, so for each star has to carry its own ones. As I mentioned before, the age is drawn from a prior, which we understand. Okay, so let's see how we do. So test one, we're using mock data from Chempy with correct yields. So we put in an IMF slope of -2.3. And this plot is showing that the inference gives us an IMF slope of -2.3, which is great. So it's suggesting that our inference works completely as expected. This is kind of not really a surprise because we're using a model to analyze data created from that model. Two salient points from this. Number one is that you notice the envelope of this function decreasing as we get to larger n stars. Here, n stars is the number of stars we used in our analysis. So 1 star here is similar to what we're doing in the protostellar abundances data. The 2, we're now including like 100, 200 different stars. And you notice that as we include more stars, the confidence shrinks. Well, we get more and more confident of our result. The statistical error just decreases and decreases, which is completely as expected. Now, I'll also like to draw your attention to the crosses here. Every single one of these crosses is the inference run with an independent set of stars. So here, down n stars of 1, what we're saying is that we have 100 individual data sets, each comprising of 1 star. So we're actually going to analyze all of them separately. And each one of these is a specific parameter that we've obtained from doing that analysis. Down to sort of 10 stars here, we have 10 independent sets of 10 stars, for example. And the reason this is important is that it really shows you the amount of bias you can get from doing an analysis looking at a single star. For example, our previous works, we've only been looking at 1 or the early papers 2 or 3 stars. However, what's to say that a single star doesn't predict you an IMF slope of down here when we know the true value was actually minus 2.3? We're getting kind of 10–20% deviations. So this kind of statistical error is actually very important. Okay, so let's analyze the second data set. This is the mock data from Chempy, this time with incorrect yields. So we use one set of chemical yields to make the data and a completely different one to analyze them. These contain none of the same yields. And what we note here is that there is a bias. And as we go to large size data sets, the bias converges. It's around 0.1 in the IMF slope. So it's around a 5% bias. This isn't really surprising because we are using a model with very different chemistry in it. For example, our first model might say, okay, we have a certain amount of iron, and the second model might say, actually, we produce double the amount of iron. And that is going to affect the parameters that we're inferring. So this is something that we have to be careful of. And in the future, when we're looking to analyze real observational data with this is something that needs very careful attention. And it's probably the idea that we should be doing this analysis using several different sets of yield tables to really give us an indication of how variable our results are. Okay, the third one I wanted to show you is using the Illustris TNG data. So this is including far more physics, but the correct chemical yields. And we notice that the parameters we get, draw attention to the blue curve first, are pretty much perfectly consistent with the true result, within 1 sigma all the way up to kind of 200 stars in our data set. And this black dotted line is the true value in our simulation. So despite the fact that our model uses the wrong physics, uses a strong simplification of physics, we are still able to obtain very good parameter constraints. So the gray and pink regions I've added on this plot, they're shown to represent the size of the error we get from contemporary measurements of this parameter in the universe. So Dan Weiss was looking at, I think, star counts in the M31 cluster, and you get slightly narrower constraints. Hosek paper is a completely different method. And you see that the error bars, even on very contemporary measurements, are still very large. And yet, our method seems to be significantly less biased, has significantly smaller errors. Now, of course, we do need to take into account the fact that we have these uncertain yields. As we could see in the previous plot, it gives kind of 5% deviation. Yet this is still completely comparable with our most up-to-date models of these parameters. So if you're interested in things like constraining galactic parameters, performing multi-star inference like this is a very powerful technique. Okay, so to kind of talk a little bit more about what I was saying before, model errors are particularly useful in terms of our analysis, especially in this sort of context. They can indicate where our yield tables are going wrong. So this is the distribution of our model error parameters for the analysis when we use the wrong yield set to analyze our data set. So for each one of these, we see a PDF of where the effective model error is for each element. So for example, for nitrogen, Hamiltonian Monte Carlo sampler spat out a result to say the model error for nitrogen is around 0.15 days. So 0.15 magnitudes of nitrogen, we just don't know it better than that. Our yield set is wrong at some level. And the reason this is interesting is because if we go and look at the two yield tables we actually used, silicon, nitrogen, and carbon are the most discrepant elements between the yield sets. So just by running a simple analysis like this, which is simply comparing mock observational data to analysis from Chempy, we can tell what the problems are with our actual yield sets. And this would be particularly relevant when we go on to apply this to actual observational data. Okay, so this multi-star inference was the result of our recent paper, but this is not all. And Chempy has many, many more areas that can be explored. So I think Jan might want to kind of give us a slight indication about what's next for Chempy.
All right. So yeah, I have to say it doesn't need to be Chempy. You can plug in any galactic chemical evolution model. Just Chempy is at our hands, so this is what we are using. Can you switch to the next slide? So exactly, because of this new technique, of this new methodology, there are lots of things that come to my mind that are possibly that can be explored. So exactly, I wanted to get a little bit of a discussion. What do you think? So Chempy can be easily extended to incorporate more complex physics. For example, a second gas phase, something like hot gas and cool gas phase in principle, or additional nucleosynthetic processes. And I'm thinking of neutron star mergers, hypernovae, or exotic types of supernova type 1a, or other supernova type 1a channels, which have different nucleosynthesis and are not taken into account yet. And I think if we want to compare it to real data, then we need to to take into account the latest, all the yield, nucleosynthetic yield channels that we think are impacting those elements that we want to run our inference on. This is one thing, and I would love to hear from you after we finish the talk. And then also I wanted to ask, because I saw those papers that are giving now stochastic or uncertainties on yield tables, and I'm not quite sure how to implement this in galactic chemical evolution models, because to me that's a methodological problem, and I just wanted to ask, what do you think? How important are they to? Because of course we could run Chempy several times and sampling from the uncertainties, but I don't know if that's a feasible approach and if that would be necessary to do. And yeah, what do you think is missing in those models? What would you think? Okay, I still don't trust this simple parameterization. Do something better. Do something more clever. So that's questions to you. Maybe after I don't know if we want to talk about it now or we want to finish. Yeah?
Probably just get to the end and then discuss.
Okay, and then discuss. Yeah, I guess that's better. All right. Then, so future projects that I see that are easily that makes sense now that we have multi-star inference. I think one good project would be to run this multi-star inference on real data to compute Milky Way simple stellar population parameters. So to infer the Milky Way IMF and the number of supernova type 1a that needs to explode. And this might be interesting. I mean, I don't know if the IMF is universal, but we could also parameterize it as metallicity dependent. And if we want to run this project, then we need to include many tests with many different nucleosynthetic yields and touch real data. So that might get a little bit dirty, but I think that's a very interesting project, because I think nobody else really has tackled it with such a strong statistical signal. Then something else would be to optimize the chemical evolution parameters for hydrodynamical simulations, including those parameters and looking for the best yield tables. So in essence, score yield tables and look for the best SSP parameters, simple still population parameters, to reproduce data that we have in order. For example, this Illustris TNG simulation will get an update eventually, and then what yield tables are they using and what SSP parameters are they running on? So before running such an expensive simulation, I think we could invest some time to try and optimize and look for the best yield table and for the most likely simple stellar population parameters. And then what would be really cool to infer yield tables empirically from observational data. But this has the problem that you cannot do it on neural nets anymore, because empirical yield tables would need to tune many parameters, and then you will have to recalculate the yields or the ISM abundances that come out of Chempy for each iteration. So it will be a little bit more costly, but it might still be very good. And I think with 200 stars or even more, you get a very strong signal. So the parameter space that is covered, the chemical abundance parameter space, should be very confining on the nucleosynthetic yield data. And yeah, so I think, of course, we don't have the nature is has a much bigger variety. So it's not really that we are tagging down and saying, okay, supernovas go off with such a yield of elements. It is closer to this basic assumption. Okay, we have general ingredients and try to resimulate the universe. So it's more an average of many different types of core collapse supernovae. Okay, so in summary, Chempy is fast and flexible, GCE model allowing for Bayesian exploration of parameter space, and we played around with it in this mathematical sense and being ignorant about nucleosynthetic yield tables. Then we have used Chempy and shown that it can optimize SSP parameters for hydrodynamical simulations and ensure that they match observational data. And I think this approach will be much stronger with more data points, because now that we can do this inference on multiple stars, global galactic parameters can be constrained really tight, and maybe even yield tables can be constrained. So
I think there's one thing I should mention at this point, is that the entire Chempy project is completely open source. So all of our code is fully available on GitHub. We have full tutorials for how to use it. There's full tutorials in how to extend it to multiple stars, how to run Hamiltonian Monte Carlo, and how to score yield tables itself. So in fact, given a set of yield tables, it's no more than a day or two's work to compute scores of how well they actually perform. And it's been designed publicly such that anybody is more than welcome to use it. And we're very happy to kind of help out with any usages. And we definitely encourage other people to use it beyond our collaboration. And I think at this point, I think we should probably wrap up. But I think we're definitely happy to answer any questions and any kind of discussion about what things from a nuclear chemical perspective would actually be useful for us to be testing to really kind of drive proper exploration of our models. So thank you very much.
Yeah, thank you both for speaking. It's hard to have applause when everyone's muted, but if anyone has any questions, feel free to jump in. Just make sure you unmute yourself first.
If there is no question, I have a question. So if we go back to this slide where we marginalize, where you score the yield tables and you show the elements, there was this magnesium and the silicon offset. This was something that really struck me, that we marginalized over all chemical evolution parameters, and there was always this offset between magnesium and silicon, and using all the latest yield, that was all the latest yield tables. So here, if you look at this plot, so in essence, the chemical evolution parameters are marginalized out, And you see that magnesium is always underabundant and silicon always overabundant. And there's really they're never at the same spot. So I was wondering, we looked in the literature for something, and I was wondering if you guys have some take on this, because so the only thing that we found was that if you lower the explosion energy of core collapse supernovae, then this silicon overabundance or magnesium underabundance is less severe or something. But maybe someone in the audience has an idea what causes this discrepancy.
Any takers? I mean, I haven't looked at those specific elements and how they're created. I work on core collapse supernova simulations, and I haven't looked specifically at how those two elements are formed and how the explosion energy plays into that. But we don't entirely understand the explosion mechanism, and our core collapse supernova models have so many assumptions in them right now that I wouldn't be surprised if there's something in there that's causing strange nucleosynthesis that is maybe not realistic coming out of these simulations. So I'm not totally shocked that there's some dependence there on the explosion energy.
Okay, yeah, that's good. So okay, but that means okay. I was thinking of if you can tie this down to explosion energy or whatever. The question for us is always, yeah, how does this translate into nucleosynthesis? I mean, I'm asking this question, but I'm usually ignorant about it. I don't know what's going on. So yeah, I was wondering if maybe. Okay, if you say that there are different, that it's not completely sure how those things explode, then that makes perfect sense. There's some other things like titanium, potassium, and vanadium are always underpredicted from core collapse supernovae. I was wondering if that's something that is debated in the community of core collapse supernova nucleosynthesis people, or yeah.
Yeah, also, we're welcome to take any other questions as well. If anybody has any.
I have a vote to cast for another additional nucleosynthetic channel. I know that like Evan Kirby has done some work recently looking at, I think, cobalt and nickel abundances as a way of testing whether double degenerate type 1a supernovae versus single degenerate. Have you thought about including separate yield tables and trying to figure out if you can work out a fraction of these different scenarios, or if one is the preferred channel?
Definitely, I think that's you just have to implement it, give another free parameter, and then whoosh, you will get your different channel fractions. So that should be doable. Yeah, just implement a new yield table, and then this would run. So what was the other? It was double degenerate versus single degenerate, and there are different yields for both. Different yield sets. So yeah, that should run. So also neutron star mergers. We didn't include our process so far, but that should also be possible.
Interesting. Anything else?
Any other questions? Well, if not, then thanks very much that we could present our work here. That was really nice. Yeah, I hope, I don't know if we were too far off or anything, but I hope that, yeah, if you feel like you want to optimize your yield tables, then please come to us. The code is public. You can also just look at it, or we are happy to help. If you think that there's a demand for somehow connecting the nucleosynthetic yield that is created from core collapse supernova explosion models to the to elemental abundance data of stars, then we have the machinery here. If you think that that would be useful for your science, just come to us.
Actually, this is Rick out of the Naval Academy. I do kind of have a question. When you were going through your IMF parameterization,
yeah,
you were looking at kind of a standard minus 2.3 slope kind of thing.
Yeah.
Can you model other IMFs? Like, I'm interested in the POP3 IMF, which some folks think might be like a log normal model. Is that easy to implement?
Yeah, that's actually incredibly easy. That's the sort of thing that can be implemented in about 10 minutes.
Yeah, I'm definitely interested in looking at your software, because I do large scale simulations, and I'm looking at the POP3 IMF and trying to constrain it by looking at those POP3 supernova yields, core collapse yields, and looking at the abundances in population 2 stars, some of the really old stars the observers have. So this seems to be kind of right up the alley of.
Yeah, no, that sounds definitely very doable and certainly an interesting exploration.
Yeah. So I'll definitely go to the GitHub and check this out.
Yeah, and definitely get in contact with us for anything.
Yeah.
And you can also, so this is also what I was thinking of, like metallicity dependent IMF. You can easily get a second parameter or even more complicated parameterization for your IMF and tie it to metallicity or to some other, to time, but I guess metallicity or some elemental fractions. Whatever you think, you can use different parameterization and change the slope over time or with metallicity. That's definitely doable. And with 200 stars, you get a very strong signal on this. So that's definitely doable.
Yeah, I'd really like to run some of my simulation data through this and see, like before when I did this, I was using Alex Hager's models for POP3, zero metal stars for my yield tables. And obviously those are about as uncertain as you can get. So
Yeah, exactly. So that's the question. You can then, with this thing, you can directly compare to the data. So that makes, that gives you, tells you how well it actually matches or could represent the real data. Yeah,
exactly. I think people like Alex Hager out there in Monash would really like to get that feedback, because we do have good observations of POP2 stars that I believe we think have only been enriched by one POP3 supernova. So we could run those tests and see what we get. So yeah, I'm pretty excited at this, guys. I'd like to make some time to look at your code and see how we can go forward.
Great.
Cool. Nice.
Yeah. Anyway.
Right, any final questions?
I guess I have one final question for Oliver.
Okay. Yeah.
You were assuming in this work the multi-star, like a 20% uncertainty on age. Do you have a sense that, like, if you had no information on, like, just completely uninformative age priors, is this technique still doable, or do you run into some problems?
Yeah, I think we did play around with this a little bit. There is dependence, and I mean the parameter constraints certainly get worse the less you know about the ages, as you kind of expect. It's certainly having some idea of the age massively helps our inference. We don't have to be particularly precise, and it's not particularly sensitive to utterly precise ages. But I think the point is really that an age of 1 gig years and an age of 14 gig years are so completely different in the code that it massively speeds us up if we don't have to explore the whole parameter space. Just focus on the regions which are actually interesting.
But yeah, I think maybe the question was also in the direction, can you infer ages for stars without knowing them? And I also asked Oliver about this, but we didn't. So in this paper, we didn't really look into this. So we didn't follow this up. But I think there might be a way to get to the ages. Yeah.
Always the questions are how degenerate are your parameters, and how much is that correlated with like IMF parameters and stuff like that. It would certainly be quite possible to, if say we knew the IMF parameters pretty well, if we could say, okay, let's set the IMF mass slope to -2.3. In that case, can we determine the ages? And I think in that case, we get a much stronger constraint. But there's certainly degenerate parameters at some level.